George Notchik here. Today I'm going to discuss some non-standard calculus. In particular, what we refer to as fractional calculus. We're going to talk about fractional derivatives in integrals. For example, what does it mean if we want to take the 1/2 integral of x with respect to x? What does this mean? Or say we want to take the 1/2 derivative of x with respect to x. What does that mean? What does it mean if we take a fractional derivative or integral of a function? Generalizing the operations of differentiation and integration to non-integral orders can be performed in a number of ways. It's not unique. There is an exponential approach that seems to give a satisfactory way of defining fractional derivatives and integrals. But the result is very limited and not very useful in my opinion. In fact, the exponential development does not lead to a consistent mathematics outside of the realm of exponentials, where the nth derivative of, say, if we're dealing with an exponential, f of x equals e to the ax, what is done in the exponential development is they just extend the normal way you derive or differentiate exponentials. For example, if we take the first derivative of e to the ax with respect to x, we get a e to the ax. And if we take the second derivative with respect to x, we get a squared e to the ax. And if we take the third derivative of e to the ax with respect to x, we get a cubed e to the ax. And so on. If we take the nth derivative of e to the ax, we get a to the n. Well, the argument that's used in this approach is say, well, for each order of the derivative, we get a to the exponent that's the same as the order. So why don't we define the nth derivative of e to the ax in this manner? Why don't we just say the nth derivative of e to the ax is just a to the r e to the ax? And I mean, that seems reasonable to generalize differentiation in this fashion. And then if you apply this to complex exponentials, where the a, for example, is the imaginary unit I, which is -1, then you can take that form and combine it with, say, e to the minus ix, e to the plus ix, combined to get sines and cosines, and see what a sine and a cosine differentiated in this manner would look like by putting together complex exponentials. And if you do that, what you end up with is this. For example, you can do the same sort of thing with integration. Is, say, the integral of e to the ax with respect to x just becomes e to the ax over a, or a to the -1 e to the ax. So you can define integration as differentiation of a negative order. We can call an integral the -1 derivative. And if we do that, then in integration, we can do the same thing. We can have fractional integrals by just raising a to a negative order of the integration that we're trying to perform. And if we do that, say, for example, the nth integral of cosine will just end up being the minus rth derivative of cosine x, and this comes out to, by combining complex exponentials, comes out to that. That is, it phase shifts the cosine function by r times pi over 2. And the graphical interpretation of this is if we start with the cosine function, then if we take the rth derivative, it shifts the cosine function when we integrate. It shifts the function to the right by pi over 2r. So the cosine function now gets shifted to the right by pi over 2r. And in a like manner, if you were to take the derivative, you'll find that the rth derivative of the cosine of x with respect to x ends up being the cosine of x plus pi over 2r, which means the cosine function gets shifted to the left by pi over 2r. So now the cosine function ends up over here, shifted by pi over 2r. So integration shifts a sinusoid, cosinusoid to the right. Differentiation shifts it to the left. And you end up with the same function, just phase shifted. Such a definition of this, exponential definition, with this purely exponential approach, one can combine all the complex exponentials to form periodic sinusoids and combine sinusoids to represent periodic functions, as with Fourier analysis. However, there isn't any Fourier representation for open-ended functions like polynomials. So they have no well-defined spectral decompositions with Fourier analysis. Of course, you could find the Fourier representation of a polynomial, such as f of x equals x, over some finite interval. You'd have to pick a finite interval in order to get a Fourier representation, a Fourier series representation of it. But what interval do you choose for performing an indefinite integration? So there's problems associated with that. The exponential definition does not work with Laplace transform theory also. It doesn't work there. So it only works within the confines of this very limited exponential definition. Now, I've seen this development in a number of places on the internet. I really don't like it. And I'm going to show you what I consider a better way for handling fractional differentiation and integration. And we get at it through the Laplace transform. Because the exponential method just fails and doesn't lead to anything. Leads nowhere. So the very useful method that I have found over the years in defining fractional calculus is through the Laplace transform theory, whereby in the Laplace transform theory, the operations of differentiation and integration are performed in the complex frequency domain. You transform your time function or your function of x into the Laplace domain, perform your integration and differentiation in the complex plane in the complex frequency domain, and then transform back. Now, when in the complex Laplace domain, if you have, say, a function of x, and you transform it. You take the Laplace transform of f of x, and this gives you a function of s. This is in the Laplace space, or what we call the complex frequency domain. Now, to differentiation in the using Laplace transforms, I've discussed this in other videos, but if I take the derivative in this domain, in our x or time domain, t domain, time domain, in the Laplace domain, it's just multiplying the transform function by s. And if I integrate f of x and operate in the Laplace domain, we just take the transform function and divide by s. And if we take the second derivative, we multiply by s squared. And if we do a double integral, we divide by s squared, and so on. What the Laplace transform does is it takes the operations of integration and differentiation and transforms it into multiplication and division. This is just like with logarithms. Logarithms are a transform. Logarithms take the operations of multiplication and division and converts it into addition and division. And Laplace transforms starts a step higher. It takes differentiation into multiplication and integration into division. So, in the Laplace domain, it makes sense then, since, say, we want to take the nth derivative of f of x, and in the Laplace domain, this becomes multiplication by s to the n on the transform function. So the natural thing to try is then saying, okay, how about if we have a fractional derivative on f of x, where r, it might be an irrational number rather than an integer, then this would just be multiplication in the s domain by s to the power r, where r is the same power as the fractional order of the derivative. And r could be an integer, then we have the standard definition of a derivative. If r is an integer, but now if r is rational or a fraction, we have a natural way in which to define how we perform that differentiation or integration. We transform the function that we want to integrate or differentiate into the Laplace space or the complex frequency domain. We perform our operation of integration and differentiation in the Laplace space and then transform back to see what the result looks like. Now, let's take a little look here. For example, suppose I have f of x is equal to x. Now when I go into the plus space, f of s just becomes 1 over s squared. X in the Laplace space is 1 over s squared. Now if I want to, say, take the 1/2 derivative, we'll call that 1, d 1/2 f of x, or this is, since f of x is x, we're taking the 1/2 derivative of x here. In the Laplace space, then it makes sense that we just multiply by s to the 1/2 of the transformed function. So this becomes now 1 over s to the 3/2. We just subtract the exponents. We just as we use the properties of exponents in a normal fashion. So what we do then is we go to the Laplace Transform pair tables and see what function of x is represented by 1 over s to the 2/3. Well, I'll get to that in a little bit, is how we can find out what function of x this is. Or suppose we want to take the 1/3 integral of f of x with respect to x. Well, we transform our f of x into the Laplace space. We find f of s, which is the inverse Laplace transform, it's the Laplace transform of f of x. We call that cap f of s. Then the integral will just be 1 over s to the 1/3 times that. We divide the function by s. Dividing a transform function by s is the same as integrating it. So we're taking the 1/3 integral, and so the power on s, rather than being 1 for the standard integration, we use the same order as the integral on the exponent for s. So then what we do is we have our transformed integral, and we look up this in our transform pair tables and find out what function of x this represents. Now to proceed in using the Laplace transform methods like this, we need to familiarize ourselves with both the gamma function and the incomplete gamma function. First, we'll look at the gamma function. We need to have an understanding of how to manipulate and calculate values of the gamma function, because it shows up all the time in the Laplace transforms. To proceed using Laplace transforms, we need to familiarize ourselves with the gamma function and the incomplete gamma function. I'll first discuss the gamma function. It's defined to be the improper integral from 0 to infinity of x to the z minus 1 e to the minus x dx, and z can be a member of the complex numbers. Now this integral is not an easy integral to integrate out into a closed form. In fact, for most values of z, this does not integrate out into a elementary functions or a nice closed form. So you have to evaluate it numerically, and most of the values for gamma z are computed numerically and tabulated. But there are special values for z in which you can get a closed form solution. Now there's some properties that are very useful in manipulating the gamma function. Now just briefly go through them. Now if z is not 0 or a negative integer, then this relationship holds. This is a reduction formula. Gamma of z plus 1 is equal to z times gamma z. And if your z is not 0, a negative integer, or minus 1/2, then this relationship holds. That gamma z times gamma of z plus 1/2 is equal to 2 raised to the power of 1 minus 2z times the square root of pi times the gamma of 2z. This is useful whenever you're dealing with multiples of 1/2. Now, if n is a positive integer, this also helps you where you're dealing with multiples of 1/2, where gamma of n plus 1/2 is 2n factorial divided by n factorial divided by 4 to the n times the square root of pi. Now here is probably the most important relationship on the gamma function, is that if n is a positive integer, then gamma of n plus 1 is n factorial. And this is where the gamma function gets a name as, also it's referred to as a factorial function. When n is an integer, gamma of n plus 1 is equal to n factorial. And if you substitute n minus 1 in for n, then gamma of n is just n minus 1 factorial. It's a factorial function. N has to be a positive integer. Now, if we put n equal to 0 in here, we get gamma of 1 is equal to 0 factorial. And we define 0 factorial as being equal to 1. Now, n has to be positive integer. If you're trying to take the gamma function of an integer, the integers have to be strictly positive. They can't be 0 and they can't be negative. That n has to be an element of the positive integers, because gamma on the negative integers and 0 are undefined. It blows up. The gamma function blows up. It's undefined on the negative integers and on 0. But for any value, negative value between the integers, negative integers, it's just fine. But it just blows up on the negative integers and 0. So you have to be careful about that. Another very useful relationship is that the gamma of 1 minus z times gamma z is equal to pi over the sine of pi z, but z cannot be an integer, either positive or negative, because this blows up. If z becomes an integer, you have the sine of an integral multiple of pi, which is always 0. So this blows up if z is an integer. But as long as z isn't an integer, this is a very nice relationship. Let's just go through a few of these. You'll notice that square root of pi shows up quite a bit. And that's when you're dealing with multiples of a half. You always end up with square root of pi, and that shows up a lot. So let's look at, here's probably the most important relationship or value of gamma you need to know, is that the gamma of 1/2 is the square root of pi. Well, let's see if we can use one of our relationships here to get it. Well, we have to use a relationship where z can be equal to 1/2. Well, z could be equal to 1/2 in this relationship. The only restriction is that it's not be an integer. So let's make z equal to 1/2 here, so we get gamma of 1 minus 1/2, which is a gamma of 1/2, which we're looking for. So gamma of 1 minus 1/2 is gamma of 1/2, and that is equal to, let's do it this way. Gamma of 1/2 is gamma of 1 minus 1/2 times gamma of 1/2. That's this relationship here. And that's equal to pi over the sine of pi times z. In this case, it's 1/2. Sine of pi over 2 is 1. So we just get pi. Well, gamma of 1 minus 1/2 is gamma of 1/2, and that's times gamma of 1/2, and that is equal to pi. This is gamma 1/2 squared, so gamma of 1/2 then will be the square root of pi. We could also, let's see, we could also use this, because positive 1/2 is not restricted in this particular relationship. Let's try this one. Gamma of z, let's put z equal to 1/2, so we have gamma 1/2 times gamma of 1/2 plus 1/2, or gamma of 1, is equal to 2 raised to the power of 1 minus 2z. Z is 1/2, so we have 1 minus 1, or 2 raised to the 0 power, times the square root of pi, times gamma of 2z. Z is 1/2, so 2 times 1/2 is 1. We have here that gamma of 1 is 1, so this goes to 1, this goes to 1, so this becomes square root of pi. So gamma of 1/2 is square root of pi. It agrees with that. How about gamma of minus 1/2? What's that value? Well, z is minus 1/2. We can't use this because that's restricted. We can't, forbidden to use it in that relationship, but we are not forbidden here. This relationship only tells us that we're restricted on the integers. Minus 1/2 isn't an integer, so we can put that in here. So rewrite this. I'm using this particular relationship. So we're going to have gamma of 1 minus a 1 minus 1/2, so that becomes a plus, times gamma of 1/2 minus 1/2. Our z is equal to a minus 1/2, and that's equal to pi over sine of pi times a minus 1/2. So this becomes pi over minus sine pi over 2. Sine of pi over 2 is equal to 1, so this becomes minus pi. And we have gamma of 3/2 times gamma of minus 1/2 is equal to minus pi. Well, we need to know what gamma of 3/2 is. Well, we could get that by using this, by putting n equal to 1. Gamma of 1 plus 1/2 is 3/2, and 1 is a positive integer, so we can use this. Let's evaluate what gamma of 3/2 is. Gamma of 3/2 equals gamma of 1 plus 1/2, and that's equal to, n is equal to 1, so we have 2 factorial over 4 to the first power times 1 factorial times the square root of pi. Well, 2 factorial is 2, 4 to the 1 is 4, and 1 factorial is 1, and that's the square root of pi, so this is square root of pi over 2. That's gamma of 3/2. Well, solving for gamma of minus 1/2 is minus pi divided by gamma of 3/2 from this equation. Well, gamma of 3/2 is square root of pi over 2, so this becomes minus pi divided by square root of pi divided by 2, or minus 2 times the square root of pi. So that's the value for gamma of minus 1/2. So that's how we can use some of these relationships to give us values of the gamma function. Now, we'll talk about a little bit about some Laplace transforms that we'll use. I've put some values for this gamma function that we'll be using. We have gamma of 1/2 is the square root of pi, and then we have gamma of 3/2, 5/2, 7/2, and 9/2. These show up quite a bit when using Laplace transforms. In discussing Laplace transforms, we need to make use of 2 functions. One is the step function, which is designated as u of x, where it's equal to 0 when x is less than 0, or say less than or equal to 0 minus, and it's equal to a 1 when x is greater than or equal to a 0 plus. Now, what it looks like is if we plot with x, the step function is 0 for negative values of x, and then on just to the left of 0, it's still 0, and then just to the right of 0, it jumps up to the value of 1. Now the derivative of the step function is called the impulse function, or Dirac delta function. It's designated as delta x, and it has a value of, well, it's the derivative of u of x with respect to x, and it looks something like this. It's 0 everywhere except right at 0, and it's an impulse. It has infinite amplitude, but yet it has a finite integral. That is, the integral of delta x, if you integrate over 0, it's equal to 1. It has an integrated value equal to 1, even though it has an infinite amplitude. And the way we generally get at that is you could define the impulse function this way, is you could create this function here where, say, the width is t and the height is 1 over t. So the area under the curve, under this, or is, we have a triangle, so the area is 1/2 base times the height. So let's make the height 2 over t. So then that comes out to 1. The area is always 1, regardless of what the width is. And then what you do is you shrink the width down, and as t, the width gets smaller, the amplitude gets bigger. That is, if, say, you shrunk it down, say, to here, then its amplitude goes up. And then it goes. And then as you shrink it, the amplitude goes up to where it has 0 width and infinite amplitude, such that the product, this is a 0 times infinity type product that is finite. The area under the curve always comes out to 1, because the height goes up in the same proportion that you shrink the width down. And that's how the delta function is defined. So it's everywhere 0 except right at 0. Now, in Laplace transforms, if you're to put these functions into the Laplace integral to get their transforms, remember the Laplace transform, if you have f of x, then this goes into f of s in the Laplace domain, which is the integral 0 to infinity of f of x times e to the minus x s dx. And what you do is you integrate the x out, and you end up with a function on s. That is the Laplace transform. That is, if we designate the Laplace transform of f of x as f of s, which is that particular integral. And if you put in the impulse and the step function in, then a Laplace transform of a delta x just becomes a constant in the frequency domain, and a u of t, the step function, becomes a over s. So basically, a constant in the x domain becomes a constant divided by s in the frequency domain. And here are some other Laplace transforms. If we were to say take x, it transforms to 1 over s squared. And x to the 1/2 goes to the square root of pi over 2 times 1 over s to the 3/2. And x to the minus half becomes square root of pi over s to the 1/2 the 3 halves becomes this. X to the 5 halves becomes 15 pi over 8 times 1 over s to the 7 halves. And here are two general formulas of Laplace transforms that we'll use. Is that if in the x domain we have x to the n over n factorial, or just say x to the n, then it becomes n factorial over s to the n plus 1, where n is an integer. So if x is raised to an integral power, this is its Laplace transform. And if x is raised to a real power, non-integer, the v has to be greater than -1. This is a restriction. Then its Laplace transform is gamma of v plus 1 over s to the v plus 1. And we can see that this reduces to this when v becomes an integer. When v is an integer, we have gamma of n plus 1. And remember, gamma of n plus 1 is n factorial. That the gamma is what we call the factorial function. So gamma of n plus 1 is n factorial, and v becomes n. So this becomes this when v is an integer. So these are common Laplace transforms. Now when you deal with more complicated functions, you don't want to be doing these integrals. There have been books published that give you what are called transform pairs. This is one such book. This is by Roberts and Kaufman, Tables of Laplace Transforms. And there's hundreds upon hundreds of pages of Laplace transform pairs. You get a function in the x domain, and you find the particular form that you're looking for, and then you just read off what the function of s is in the Laplace space or in the frequency domain. And then to go back, you look at the transform pairs. There are functions of s where you're in the Laplace space, and then it tells you what the corresponding function is back into the x domain. So you don't, when you're dealing with Laplace transforms, you're not going to be doing these integrals. You want to have a table of transform pairs like this. That makes the work very easy for you. Now, let's talk about the 1/2 derivative of a function, now that we have our basics down. Let's look at what the 1/2 derivative of x is. So we're going to take the 1/2 derivative of x. Okay. Well, first thing we do is we transform our function x into the Laplace space. Well, x is to the first power. So x to the first power just becomes 1 factorial over s to the n plus 1. N is 1, so it's 1 over s squared. So x becomes 1 over s squared. That's the transform of x. And then we're going to perform our differentiation in the Laplace space, which is s to the 1/2. We multiply the function by s to the power of the order of the derivative that we're taking. So if we're taking the second derivative, we'd multiply by s squared. If we were taking the first derivative, we'd multiply by s to the first. So this now becomes, with the power of exponents, 2 minus 1/2 in the denominator becomes, this is s to the 4 halves minus 1/2, or s to the 3 halves. Well, that's the function value in the Laplace space. So we need to find the inverse transform, and we can use this. See, we have s 1 over s to the 3 halves. So that is x to the 1/2 times 2 over the square root of pi. We want to get rid of this constant here. So we have x to the 1/2. That goes in the Laplace transform as pi 2 times 1 over s to the 3 halves. But we don't have pi over 2 times s to the 3 halves. We just have 1 over s to the 3 halves. So we multiply both sides by 2 over the square root of pi. To get 1 over s to the 3 halves. All right, well, this is the value of the function in the frequency domain. In the time domain, that is our function. So, the 1/2 derivative of x, what a mess. I'm afraid my pen is going on me. Use a different pen here. So, the 1/2 derivative of x then is 2 over the square root of pi x to the 1/2. So that's the 1/2 derivative of x. Let's look at what is the 1/2 derivative of a constant. Now remember, with normal derivatives, the derivative of a constant is 0. That is, we have if we have a constant a, then the derivative of a with respect to x equals 0 with a full derivative. What about the 1/2 derivative of a? Is that 0? Well, let's check. Well, in the Laplace space, a goes to a over s in the Laplace domain. Then, to take the derivative of a, the 1/2 derivative, we multiply this. So we're taking the 1/2 derivative, so we multiply this by s to the 1/2. So this becomes a over s to the 1/2. Well, now let's find what function of x this is the transform of. Well, looking down in here, we see we have an s to the 1/2 here. So x to the minus 1/2 transforms to square root of pi over s to the 1/2. This is a transform pair. So if I divide each side by divide by square root of pi, this becomes 1 over s to the 1/2. Well, we're almost there. We have in the transform space a over s to the 1/2. We know now that 1 over s to the 1/2 transforms to 1 over square root of pi x. I'm just putting the x down under the square root sign with pi. 1 over s to the 1/2 transforms to 1 over square root of pi x. So a times becomes that. So the 1/2 derivative of constant does not vanish to 0 like it does with a full derivative. It goes to a over square root of pi x. Well, we might think, well, what might happen if I take a 1/2 derivative of this to get a full derivative? We have a half derivative of a. If we take another half derivative of a, we should have a full derivative. Well, let's see what happens if we do that. So we just determined that the 1/2 derivative of a with respect to x equals a over the square root of pi x. Now, let's take the half derivative of this. So we're going to take the 1/2 derivative of the 1/2 derivative of a with respect to x we're doing it twice. So we would expect that this should be just the derivative of a with respect to x. We're taking two 1/2 derivatives, so that should give us the full derivative. Well, we need to transform this into the Laplace space. Well, this becomes what? This is a over square root of pi times 1 over x to the 1/2, or this is a square root of pi x to the minus 1/2. Well, we see here that x to the minus 1/2 transforms to square root of pi divided by s to the 1/2. So this then transforms to, we have a over the square root of pi times the transform of x to the minus 1/2, which is square root of pi over s to the 1/2. The square root of pi's go out, and we end up with a over s to the 1/2. Well, now we take the 1/2 derivative of this, and when we take the 1/2 derivative, we multiply by s to the 1/2. The s's to the 1/2 go out, and what do we have left? We have a, but if you remember, a in the transform space is a times the delta function on x in the x space. Well, this is 0 everywhere except at x equals 0. So this is going to 0 like the full derivative did. When we take a full derivative on a with respect to x, we get 0. Well, we can express 0 as a delta function because the delta function is 0 everywhere except at x equals 0. So indeed, we do get 0 when we differentiate a constant 1/2 times twice. Now, let's look at a few other functions, and then we'll look at integration in the Laplace space with fractional integration. Now, let's look at taking the 1/2 derivative of x to the p, where p is any real number greater than minus 1. So we're going to take the 1/2 derivative, and p is going to be any real number greater than minus 1. And p will be in the real number system. So p could be a third, it could be pi, it could be any real number, as long as it's greater than minus 1. And you'll see why that's true here. Now, the derivative, 1/2 derivative of x to the p, we first transform x to the p into the Laplace space. Well, x to the p, we would use this. V can be any real number greater than minus 1. See, that's the restriction I have here. So I can use this particular transform pair. Well, x to the p in the Laplace space becomes gamma p plus 1 over s to the p plus 1. And p has to be greater than minus 1. Now, to take the 1/2 derivative, so if we're going to do the 1/2 derivative of x to the p with respect to x, then that goes to, we take the function in the Laplace space, the transform of x to the p, and multiply by s to the 1/2. So then this becomes gamma p plus 1 divided by s to the p, and we're subtracting 1/2 from 1, so it's s to the p plus 1/2. Now that we've performed the integration or a differentiation in the Laplace space, we go back now to the x space to see what function this is. Well, we can use this again. We see that in this case, what we're going to do, our v becomes p minus 1/2. See, what we have is p plus 1/2, and we want to make use of this transform pair, so we have to equate p plus 1/2 to v plus 1. So this will tell us what our v needs to be. V then will equal p plus 1/2 minus 1, or p minus 1/2. So when we make that substitution here, we have gamma v is p minus 1/2 plus 1, so that becomes p plus 1/2, and over s to the p plus 1/2. And that transforms to x to the v. V is p minus 1/2. Now, we're almost there. We see that we need to find what this function in the Laplace space transforms into the x space. Well, we have 1 over p plus 1/2, but the numerator isn't quite right. So what we have to do then is divide through each side here by gamma over p plus 1/2. I'm just moving that down. So now we have this. This function of s transforms to this in the x domain, but in the numerator we have a gamma times p, or gamma of p plus 1, so we put a gamma of p plus 1. So the 1/2 derivative of x to the p is this function. It's x to the p minus 1/2 times gamma of p plus 1 over gamma of p plus 1/2. Now, let's make a substitution to see if it agrees with what we just did. We just found, remember, the derivative of x, the 1/2 derivative of x. Well, in this case, what we could do is just make p equal to 1 to get the 1/2 derivative of x with respect to x. In the general form here that we determine with x to the p, we just make p equal to 1. In that case, if we make p equal to 1, we get x to the 1/2 gamma of 2 over gamma of 3/2. Well, gamma of 2 is 1. Gamma of 3/2 is square root of pi over 2. So then this becomes x to the 1/2. Gamma of 3/2 is square root of pi, and we bring the 2 on top. And that's what we just calculated before. So it checks out. Now, what happens if p is an integer? we can reduce this further. If our power on x is an integer, the power p is an integer, then we can reduce this further. Is what we had was the 1/2 derivative of x to the p is equal to x to the p minus 1/2 gamma p plus 1 over gamma p plus 1/2. We just figured that one out. Now, suppose p equals n, which is an integer. Let's say a positive integer. And in that case, we have derivative of x to the n, 1/2 derivative, then becomes x to the n minus 1/2 p to the n plus 1, or gamma to the n plus 1 over gamma n plus 1/2. Well, from some of our gamma function properties that I gave previously, we can reduce down our gamma functions. Remember that gamma n plus 1 is n factorial. So we have x to the n minus 1/2 times n factorial over gamma n plus 1/2 is 2n factorial times the square root of pi over 4n n factorial. So we'll have an n factorial squared. So when x has a integral power, and we're taking the 1/2 derivative of it, this is what we end up with. We have x to the n minus 1/2 n factorial squared 4 to the n divided by square root of pi divided by 2n factorial. So you can see that it's not quite so easy as it was with full derivatives. With a full derivative on x to the n, this just becomes, we bring the power down and we reduce the power on the exponent by 1. Very simple. Whereas with a 1/2 derivative, it's not quite that simple. It's not intuitive as to what you're going to get. The only thing that's intuitive is we reduce the power of n by the same as the order on the derivative, just like we did here. We're taking the full derivative on x to the n, so we reduce the power by 1. Here, we're taking the 1/2 derivative on x and we reduce the power by 1/2. But the constant that goes out in front is not the 1/2 or the n that we had with the full derivative. We end up with something fairly complicated. Now we'll look at integration.